Hello students, in this lecture we will study first order systems connected in series. Now there are many physical examples where we can represent several first order systems in series. The perfect example is your liquid level tank. Now two liquid levels, they can be connected with each other in different arrangement. One such arrangement is the arrangement as shown in figure A. Now in this is tank 1 and this is tank 2. The height in tank 1 is h1 with uniform cross sectional area h1. The tank in height 2 is h2 and the area is a2. Now this is q, this is q1, this is q2, this is resistance 1, this is resistance 2. This type of arrangement is known as non-interacting systems. And the second type of arrangement is the one where again both the tanks are connected in series, but the arrangement is somewhat different. This is a resistance 1, flow rate 1 flowing through this. This is a resistance 2, flow rate is q, the input is this, the height is h1 with the cross sectional area a1, that is tank 1. Tank 2, the height is h2 and area is a2. Now this type of arrangement is known as interacting systems. So we have non-interacting systems and we have interacting systems. Now what's the difference between these two arrangements? Now you see, now in the first arrangement, that is over here, if I suppose close this valve, what will happen? If I close this valve, what will happen? The tank will fill up and it will try to overflow it. Does it affect the dynamics of tank 1? No. That means if you change the output of the tank 2, it doesn't affect the change in tank 1. So that's why the name comes non-interacting. That means the dynamics of second tank does not affect the dynamics of the first tank. Clear? Whereas in the second figure, that is figure B, now if you close this valve, what will happen? Once this valve is closed, it will try to, and it will, like when it reaches at the top, it will try to block this flow which is coming from tank 1, and slowly it will affect the liquid level in the tank 1. So that means the dynamics of tank 2 affects the dynamic of tank 1. So this type of arrangement is known as interacting. That means indirectly tank 2 will affect my tank 1 dynamics. So that is interacting systems. So there is a very clear difference between the non-interacting systems and interacting systems. Now for both these systems, we will try to determine the transfer function, and let's see what's the difference in their response also. Which one is more faster, which one is more quicker, which one is more sluggish in nature, or sluggish means slow in nature or slow to respond. So let's take first, that is your non-interacting systems. Okay, non-interacting. I have to plot the figure again. Now first is your non-interacting systems. Now for non-interacting systems, again we're gonna make a plot. Tank 1, input Q, resistance is R1, flow rate is Q1, resistance is R2, flow rate is Q2. The height in the tank is h1 with the cross sectional area a1. Height in the tank 2 is h2 with the flow rate a2. Clear? Now what we're gonna do is we're gonna determine H2S by QS. That means the height in tank 2 with change in Q. If suppose if Q over here changes, if there is any disturbance over here, how does the height in the tank 2 gets affected? That is what we're going to determine over here. That is H2S by QS, or we're going to find out Q2S by QS, or that is how does the outlet flow rate of second gets affected when there is change in the input. Okay, now for tank 1, we're going to write the balance Q minus Q1 is equal to A1 dH1 by dt, and we know that Q1 is nothing but H1 by R, which we did for a single tank system. So we know that it is nothing but your Q, your Q1 Q1S by QS will be nothing but 1 upon tau 1S plus 1, where tau 1 is nothing but A1 R1, right? Similarly for tank 2, we can write it for tank 2 also. For tank 2, it will be Q1 minus Q2 equal to A2 dH2 by dt, and what is Q2? Q2 is nothing but H2 by R2. Take the Laplace inverse, so we have H2S by Q1S, which is R2 upon tau 2S plus 1, where tau 2 is nothing but A2 R2. So that is number, let's say this is number 1, this is number 2. So if you multiply 1 and 2, so what do you have? So if you multiply 1 and 2, we have H2S by QS, which will be H2S by Q1S into Q1S by QS, which comes out to be R2 over tau 1S plus 1 into tau 2S plus 1. Or if you divide both sides by R2, we're gonna have Q2S by QS, which is 1 over tau 1S plus 1 into tau 2S plus 1. Clear? So that's the transfer function. Now what do you notice over here? It's nothing basically, it's basically the product of two tanks in series. This was the transfer function of the first order for the tank 1, this is for the tank 2. So basically if the two tanks are connected in series, the transfer function simply gets multiplied. If they are connected in non-interacting ways, the transfer function gets connected in series. Now suppose if there is a third tank over here, so we can write the transfer function for the third tank. We know it will be again of first order. So for them, so the overall will be the transfer function of 1 into transfer function of second into transfer function of the third tank. So this is how you're gonna get your transfer function, the transfer function for your non-interacting systems. Clear? Now over here, now suppose let's try to compare the response of this this system with a single tank. Now let's try to compare this tank with a single tank. Okay, the response. Now for that, let's assume that we have tau 1 as 0.5 and we have tau 2 as 1 and we have R2 as 1. So now we're going to compare the response of two tanks in series, non-interacting, with single tank. Let's compare the response to unit step change in input. If there is unit step change in input, how does the H2T changes? How does the height varies? Clear? So that means instead of this, we're going to use this expression. Now we know that H2S over QS is nothing but R2 over tau 1S plus 1 and tau 2S plus 1. Now we know the values of tau 1, tau 2, R2, and we know QS is 1 by S. So take the Laplace inverse, and we can find out your H2T. Clear? Your H2T. Okay, before with that, let me solve it for, let me show you what is H2S. Your H2S will be something like S2S plus 1 into 0.5S plus 1. You can take the partial fractions. .5 0.5S plus 1, solve it for ABC. Clear? And then you have your H2T. Your H2T will come out to be 1 minus 2 E minus T plus E minus 2T. That's your H2T. Now for single tank, we have H1S by QS, which is R1 over tau 1S plus 1. Clear? Now for single tank, QS is 1 by S, and let's say R2 is also, you can take R1 and R2 is same, so we have the height response comes out to be so what will be HS will be 1 over S into S plus 1. Take the partial fractions, so HT and this comes out to be 1 minus T. Now this is your response of single tank. That's the response of two tanks in non-interacting series. Now if you plot, that's the time and the response over here. Let's say this is the response of single tank, and if you plot for different values of T, so that will be response of two tanks in series. And suppose if there is third tank, then that will be this thing, so 3 tank in series. And if there is another tank, so if there is another tank, so for another tank, let me represent it something like this. So if there are 4 tanks in series, so what do you notice? Single tank is quicker than 2 tanks in series, and 2 tank is quicker than 3 tanks, and 3 tanks is quicker than the 4 tanks. So obviously if you go on increasing the number of tanks, the system becomes more and more sluggish in nature. That means if you see over here, if there is a single tank, let's suppose if there is a single tank, whatever change occur over here, whatever the changes occur over here, it can quickly be reported over here. But if there is 2 tank in series, the change over here will first affect the change over here, this will slowly affect the change over here. Clear? Now if you're gonna add more and more tanks over here, that means the output of the last tank will be very slowly affected if there is any change in the input. So as the number of tanks increases, this system becomes more and more sluggish in nature. So remember this. So if there is more and more number of tanks, so system becomes more and more sluggish in nature. Now suppose that means if it is tank 1, so it is 1 over tau s plus 1. Then there is another tank, tau 2s plus 1, and then there is so on n number of nth tank, so it is tau over tau n plus 1. So what will be, let's say this is qns and this is q naught, let's say input, so qns over q naught s will be nothing but the multiple of all these. So multiple of first tank, so that's the sign of multiple, that is I is equal to 1 to n, where you can say r I over tau I plus 1. So that means the transfer function of first gets multiplied by transfer function of second, by third, by fourth, and then by n. So the overall transfer function will be the multiple of the individual transfer functions of the individual tanks. Clear? Now comes your next system, which is the interacting systems. Now in interacting systems, we know that the output of tank 1 goes into tank 2. Let's say this is H1 with the cross sectional area A1, resistance R1, Q1, resistance R2, Q2, tank H2, area A2, and that's a Q. Clear? Now for this thing, again the things are quite a bit different from what we did for non-interacting systems. Let me add 2-3 slides before moving towards solving this thing. Now let's write down the mass balance for tank 1. Now for tank 1, it is Q minus Q1 equal to A1 dH1 by dt, which we are familiar with, and for tank 2 it is Q1 minus Q2 equal to A2 dH2 by dt. Clear? And under steady state, it is Qs minus Q1s equal to 0, and it is Q1s minus Q2s equal to 0. Further, Q1, in this case, it is nothing but the difference of H1 minus H2 by R1, R1, and over here Q2 is nothing but it's simply H2 by R2. Clear? So now for 1, 2, 3 and 4, let's rewrite them in form of a deviation variable. So in a deviation variable, they can be written as simply as capital Q minus Q1 equal to A1 dH1 by dt, and Q1 minus Q2 equal to A2 dH2 by dt. And what is Q1? That can be written as H1 minus H2 by R1, and Q2 can be written as H2 by R2. Now if you take the Laplace of all these four in the Laplace form, they will be like Qs minus Q1s equal to A1s H1s, let's name it as 1. So Q1s minus Q2s equal to A2s H2s, that's number 2. R1 Q1s equal to H1s minus H2s, that's number 3. And similarly H2 Q2s equal to H2s, that is number 4. Now we're going to try to solve these equations to get the final expression for your H2 over Qs. That is what we need to find. Now for this, what we're going to do is we're going to follow a few steps. Now remember those steps. Now in order to solve this thing, let me copy these 4 equations because they are important one. Okay, they cannot be copied down. So what we're going to do is simply note down that add 1 and 2. Now we need to add equation 1 and 2. Now upon adding 1 and 2, what we see is Q1 gets cancelled with Q1, and we'll have Q minus Qs minus Q2s on the left hand side, and on the right hand side we'll have A1s H1s plus A2s H2s. Okay, so let me write it down over here. Upon adding 1 and 2, so we have Qs minus Q2s, and s is common, which can be written as A1 H1s plus A2 H2s plus 1. Now from equation 3 and 4, equation 3 will substitute the value of H1, and substitute the value, and from equation 4 will substitute the value of H2 in this main equation. We're going to replace your H1 from equation 3 and H2 from equation 4 over here. So from equation 3 and 4, the left hand side remains the same. We're going to change the right hand side, so it is S into A1 into your R1 Q1S plus H2S plus A2 into R2 your Q2S. Clear? Now we're going to open up the brackets. So we have S into A1 R1 Q1S plus A1 H2S plus A2 R2 Q2S. Clear? Now from equation 2, that is from equation 2, we're gonna put the value of Q1. What will be Q1? Q1 will be A2S H2S plus Q2 over here. We're gonna put Q1 value over here. So if you, upon substituting the value of Q1 from equation 2, it becomes S times A1 into A1 R1 into A2S H2S plus Q2S plus A1, rest of the terms as it is, plus A2 R2 Q2S. Now we're going to open up the brackets, and upon rearranging, we have A1 R1 A2S H2S plus A1 R1 Q2S plus A1 H2S plus A2 R2 Q2S. Now what do we have over here? We have Q2 terms. We're going to combine them. So A1 R1 A2S H2S plus A1 H2S plus A1 R1 plus A2 R2 into Q2S into this thing. Now from equation 4, that is over here, what is the value of Q2? Q2 will be H2 by R2, that we're going to replace over here. So from equation 4, we'll find Q2 and substitute over here. So upon substituting, on the left hand side it was this term. Now on the right hand side it was, we have this term, that is A1 H2S plus A1 R1 A2, okay, S, we have S over here first, into H2S plus substituting the value of Q2, so that is H2S over R2 into A1 R1 plus A2 R2. Now over here Q2 can also be replaced by H2, so we'll replace this term also over here, that is H2S by R2. Clear? Now this H2S by R2 can be taken on the other side, so what we have is QS over here, and this term can be taken on the other side, so this becomes S times A1 H2S, and we can multiply by, you know, R2 from both the sides, so R2 plus A1 R1 A2 R2 S H2S plus H2S into A1 R1 plus A2 R2 into H2S, and multiply R on both sides, so obviously this gets also multiplied by R2. Now what do you have? H2 common, H2 H2 and H2. So H2 can be taken out, so this becomes R2 into QS, and H2 becomes common outside, and what we have inside is S A1 R1 R2 plus A1 R1 A2 R2 A square plus A1 R1 plus A2 R2 S plus 1. Clear? So now what will be H2S by QS? This is nothing but R2 over A1 R1 A2 R2 S square, that is this term, plus A1 R1 plus A2 R2 plus A1 R2 S plus 1. So what is this? Okay, I'm going to take it on the other side, on the page. Okay, now let me write it on the other side also, on the next page. So finally we have H2S upon QS as R2 upon A1 R1 A2 R2 S square plus A1 R1 A2 R2 plus A1 R2 S plus 1. Now what is A1 R1? Tau 1. A2 R2 tau 2. So this term can be written as R2 over tau 1 tau 2 S square plus tau 1 tau 2 plus A1 R2 S plus 1. So this is the transfer function for your interacting systems. Now if you compare this one with the non-interacting, now for non-interacting, your H2S by QS was R2 over tau 1S plus 1 into tau 2S plus 1. If you multiply this term, so it becomes tau 1 tau 2 S square plus tau 1 plus tau 2 S plus 1. Now what difference you find out between interacting and non-interacting? So in interacting system there is an additional term which is appearing over here. Now this additional term is called as loading, which makes the difference between the interacting and non-interacting. So this is your loading term which differentiates the non-interacting from the interacting systems. Now let's find out out of interacting and non-interacting, which one will be more sluggish in nature. For that, again, let's consider the same values of tau 1 tau 2 which we have taken in the previous case. That is, tau 1 was 0.1, tau 2 is 1, and R2 was 1, and let's say A1 is same as A2. So tau 2 is nothing but A1 A2 R2, which is 1. So R2 is 1, so A1 is also 1, A2 is also 1, so A2 and A1 is same. Clear? Now what for interacting systems? For interacting systems we have H2S by QS, which was nothing but R upon tau 1 tau 2 S square plus tau 1 tau 2 plus A1 R2 S plus 1. Now substitute the values of tau 1 tau 2 A1 R2, and we have, that is 1 over 0.5 S square plus 1.5, sorry, 2.5 S plus 1. Clear? Now that is H2S by QS. Now for unit step of in the Q, so your H2T comes out to be, if you take this thing, okay, I'm going a bit fast, let me slow it down. Now what will be H2S? What H2S will be S times 0.5 S square plus 2.5 S plus 1. Now you can solve this thing. What I did is, basically it's a quadratic, can be split into two parts. So those two paths are s plus 0.438 and into s plus 4.56. Clear? Now you can partial fraction a by s, b by this, c by this, find out the values of a, b, c, and your finally your h to t comes out to be 1 minus 1.11 e minus t by 4.56 minus 0.11, writing it quite far, minus 0.11 e minus t by 0.44. Clear? That was h to t. Now if you're gonna plot this thing, this is your time and that's your response, so it comes out to be something like this. So this is your interacting systems. Now if you compare with the non-interacting is a bit faster, so that's the response of non-interacting systems. And a single tank is much faster, so that is single tank. So remember this, single tank is more faster, quicker in response in comparison to non-interacting, and non-interacting is a bit faster in comparison to interacting. So that means interacting systems are more slow or sluggish in nature in comparison to non-interactings or single tanks in systems. Clear? So these are the few examples which we are familiar with, which will even be solving, will be doing the practical part in the lab for these two systems, for non-interacting and for interacting systems. Clear? Now if you have any query related to tanks in series, either interacting or non-interacting, you can contact me. Okay, my email ID is there. You can refer to chapter number 6 of your book for further query. Thank you so much.